I'm Akinobu Shibata from National Institute for Material Science in Japan. Today I will talk about the local crack arrestability of a hydrogen-related intergranular fracture in Martensitic steel. For hydrogen-related fracture in steels, two typical fracture modes have been recognized. One is the intergranular fracture, the other is the closed-cleavage fracture. Intergranular fracture is one of the typical brittle fracture mode, and fracture occurs at subspecific boundaries. On the other hand, closed-cleavage fracture is not so common fracture mode, and fracture occurs in a transgranular manner, but not on cleavage plane. Usually, the occurrence of this intergranular fracture leads to more severe brittle behavior. In Martensitic steel, there are several types of high-angle boundaries, such as the block boundary and packet boundaries, in addition to prior boundaries. But hydrogen-related intergranular fracture mainly occurs at the prior oxide boundaries. So here I briefly explain what is a prior oxide boundary. Prior oxide grain boundary is, as its name suggests, the position of a grain boundary in the parent oocyte state before Martensitic transformation. Because the several Martensite variant nuclei at oocyte grain boundary, and also the growth of the Martensite variant stopped at the oocyte grain boundary. So the prior oocyte grain boundary exhibits an inhomogeneous structure. For example, from the viewpoint of the misorientation, grain boundary in oocyte with single misorientation is divided by several grain boundary segments, different misorientation by Martensitic transformation. We call the unit of a prior oocyte grain boundary divided by Martensite variant as a boundary segment. For hydrogen-related intergranular fracture, the primitive mechanism itself is very straightforward. The reduction of cohesive energy of a prior oocyte grain boundary by hydrogen. But the prior oocyte grain boundary, which is the crack propagation path, exhibits an inhomogeneous structure like this. So the crack propagation behavior should be very complicated. So in order to understand the origin of a macroscopic mechanical properties of hydrogen brittlement, it is very important to understand the crack propagation behavior. So today I show the hydrogen-related intergranular crack propagation behavior in Martensitic steel, investigated by the multi-scale 3D analysis using the X-ray CT and FIB SEM serial sectioning and advanced TM analysis using the STM and ACOM TM. And these are the experimental procedures. We use the model steels, 8 nickel, 0.1 carbon as quenched Martensitic steel. As shown in this SEM image, this steel exhibits intergranular fracture even in uncharged state. So by using this steel, we can study the effect of hydrogen on intergranular fracture behavior directly. And mechanical properties are evaluated by the fracture toughness test using the compact tension specimen. And for crack analysis, we use these techniques. So from next, I show the experimental result. First, I want to briefly explain the mechanical response of the hydrogen-related intergranular fracture. This is the crack growth resistance curve obtained by the unloading compliance test, so-called the J delta curve. J is the J integral value, and delta A is the crack extension length. For hydrogen charged specimen, cracks start to propagate at very low J integral value compared with uncharged specimen. But after cracks start to propagate, the slope of this J delta A curve is not zero, but have a positive value. This indicates that the hydrogen-related fracture, even intergranular fracture, is not completely unstable premature fracture, but a kind of the stable crack propagation stage exists like this. And this graph shows the change in tearing modulus with the hydrogen content. As you know, tearing modulus is a parameter representing the crack growth resistance according to this equation. Tearing modulus, that is the crack growth resistance, decreases like this with increasing the hydrogen content. But even when the hydrogen content is high, as much as 48 ppm, still a certain crack growth resistance can be confirmed like this. So we are now considering that this could be attributed to the intrinsic crack growth resistance at a microscopic level. Next, I show the macroscopic 3D analysis result by X-ray CT. These are the X-ray CT images around the macroscopic crack tip of the uncharged specimen and the hydrogen charged specimens. Yellow arrow indicates the position of the uncracked ligament. That is the position where the crack is not continuous. So crack was arrested locally at these positions. So by comparing between uncharged specimen and hydrogen charged specimen, it is clear that the area of the uncracked ligament is much smaller in the hydrogen charged specimen. This indicates that more continuous crack propagation occurred. Okay, next I show the microscopic 3D analysis result by FIBSM serial sectioning. Unfortunately, this movie doesn't work, but this movie is very great, but unfortunately, this doesn't work. So from these results, we can know that the crack tip is not blunted. And yellow arrows indicates the position of the uncracked ligament. So very fine nanometer scale uncracked ligament exists. Today, I don't show the result of the uncharged specimen, but this kind of the very fine uncracked ligament cannot be observed in the uncharged specimen. And in this figure, the crack opening displacement is represented by changing color according to this color. The crack opening displacement is not uniform, even in one continuous intergranular crack component. Particularly, the opening displacement is very small around the uncracked ligament. And very important point is the crack tip morphology is very irregular. These findings suggest that the character of each boundary segment greatly affects the crack arrestability. Next is the crystallographic analysis result by 3D EBST. In this image, blue is the intergranular crack component, and red is a Koji cleavage crack component. So we can find that on this boundary plane, crack frequently deviated from the prior centigrade boundaries. And for this region, we measured the misorientation of existing boundary segment. And this is the misorientation profile. Misorientation is represented by the height of the bar. And this red bar indicates the position of the uncracked ligament. Again, the position where the crack is not continuous on this boundary plane. Although some boundary segment with large misorientation is involved, but basically this uncracked ligament corresponds to the grain boundary segment with small misorientation and sigma 3 segment. So we can say that in the case of the hydrogen-related intergranular fracture, very fine low-angle boundary segment could act as an obstacle to crack propagation. Next, I want to explain the local plastic deformation behavior around the arrested intergranular crack tip. As shown in this SEM image, ultra-fine grained structure with grain size less than 1 micrometer are formed around the intergranular crack. Here is the intergranular crack. And this is a 3D EBS orientation map of the same area. From this arbitrary section, we can consider that in this analyzed volume, crack propagation direction is plus Z direction, and opening displacement is very large. So at the tip of arrested intergranular crack with a large opening displacement, plastic deformation large enough to form this kind of the ultra-fine grained structure sometimes occurred locally. Next is the local plastic deformation behavior analyzed by STM. In this area, intergranular crack propagated like this. Then at this position, crack deviated from the prior authentic grain boundary and propagated grain interior as a Koji cleavage crack. And this is a local orientation map obtained by ACOM-TM around the Koji cleavage crack tip. Here is a Koji cleavage crack tip. The region far from the crack tip along a line 2 misorientation is about 1 to 2 degrees. On the other hand, along a line 1, the orientation changes significantly up to 10 degrees towards the crack tip within 1 micrometer. So this indicates that the plastic accommodation occurred in a localized region around the crack tip. So next is a high magnification STM image around the crack tip, bright field image, and dark field image. So low energy dislocation structure, so-called LEDs, as well as the curved and tangled dislocations are observed. So the deformation microstructure is well developed around the Koji cleavage crack tip. So finally, I want to briefly discuss the crack propagation behavior in hydrogen brittlement. Because of the high cohesive energy of low-angle boundary segment, crack is arrested at the low-angle boundary segment. But the obvious crack tip blunting does not occur. and crack can continue to propagate grain interior as a Koji cleavage crack. This could be the reason for the macroscopic continuous crack propagation in hydrogen brittlement. And intense localized plastic deformation is involved in both the arrest of the intergranular crack and propagation of the Koji cleavage crack. So a certain degree of the crack loss resistance that were confirmed by the mechanical test could be attributed to local plastic deformation involved in both the arrest of the intergranular crack and the propagation of the Koji cleavage crack. So this is a summary of my talk. I